So we're going to talk about net forces. So just doing a basic introduction to what force is and what net force is. And then talking about weight, specifically like how weight plays into net forces. So first, what is weight? Weight is the force due to gravity. So force due to gravity. So what is a force? It is any push or pull. So that's your definition of force. And weight is the pull of gravity. Hence, it is the force due to gravity. So weight is the pull, which makes it a force. So then what is equilibrium? So equilibrium is when all forces acting on an object add to zero. So this is just like in chemistry when we talked about equilibrium, where reactants are equal to products. Same thing happens here. It's where one force is going in one direction and there's another force to perfectly counteract it in the other direction. And so this is whenever your net force, why don't we define net force? So F net, which is net force, is the resultant force. Remember that word, resultant force on an object. So this is whenever you do your vector addition on all forces acting on it, and whatever is left over is your net force. Okay, so when all forces acting on it add to zero, that's your equilibrium. And so if the forces add to zero, then that means your F net is zero. So at equilibrium, your F net is equal to zero. So if the weight of an object is 30 newtons, what upward force must be exerted for an object to be at equilibrium? So if we were to just draw a quick free body diagram of this, we have the weight of 30 newtons, which would be going down. We need to know what upward force must be exerted. So if our F net is equal to zero, that's going to equal the weight minus this force up here. So I'm just going to say force question mark. And so if we have 30 and we want an F net of 0, then that means our question mark would also have to be 30 newtons. So 30 up, 30 down perfectly counteract each other for equilibrium. All right, so net force is the sum of all the forces acting on an object. So for equilibrium, what is the net force? F net is equal to 0. And notice here we're saying net, not N. Fn is the normal force. Here we're talking about the net force. So the net force in equilibrium is 0. Force is a vector quantity, which means it has magnitude and direction. So magnitude and direction. So you have to take into account the directions of the forces, and the direction is always in the direction of the largest force. So that's just like when we were talking about displacement, when we were talking about velocities. Everything is always in, the net is always in the direction of the largest. All right, so why don't we try a couple of examples then for net force. So a 5 Newton force and a 9 Newton force oppose each other. What is the net force? Well, let's go ahead and draw a free body diagram just so that we have completeness here. So they oppose each other, which means they go in opposite directions. One force is 5 newtons, the other force is 9 newtons. Since they're going opposite directions, you will subtract. So F net is equal to 9 minus 5, which would be 4 newtons. Now, if it told us that the 5 Newton was to the left and the 9 Newton was to the right, then assuming our picture here, this would be going to the right, always in the direction of the largest. See, this one says a crate is pushed by 2 people. One person pushes with a force of 15 newtons to the left, Okay, so let's go ahead and draw that in. So here's our box, and we have 15 newtons going this way. The other pushes with a force of 14 newtons to the left. So now they're both going left. Alrighty, let's put our second arrow, and let's flip it around. That one is 14 newtons. And so now what is the net force? Well, since now they're going the same direction, we're going to add. So F net equals 15 plus 14, which gives us 29 newtons, and that is also to the left. What upward force would be required to counteract a 10 kilogram object's weight? So now this is not the weight. Kilograms measures mass. Remember, kiss my mass. So 10 kilograms is the mass, so that goes inside the box. 10 kilograms. So which direction does weight go? Weight goes down. It's the force due to gravity. So it's a downward arrow. And then how do we find the weight? Equals mg. So m is 10, g is 9.8, and so we get a weight of 98 newtons. And it says what upward force would be required. So we have an upward force as well to counteract it. So since we have a down arrow of 98 newtons, we would need an up arrow of 98 newtons to perfectly counteract it. So this is the classic sign is hanging by strings. Now we're really only going to talk about this conceptually, so don't worry about having to solve anything or anything like that. So no worries. So again, we have our box, and let's say we have a weight. So why don't I write that in? So a weight of 2 newtons. So a very light sign. So the weight is a force, so that's an arrow. In fact, it's the downward arrow. And so then we'll label that. So that's 2 newtons. If we had one string holding it up, how much force would that string have to have? Well, to perfectly counteract it, it would have to have, see, so that would be 2 newtons. Now, since it's on a string, we call that tension. So Ft is the tension force. And this is specifically for on a string or some sort of suspension. So it's actually being held by a string. So the tension in the string. Or here it could be a chain or a rope or something like that. So now, what if instead we have 2 strings that are holding it up? Well, for the sign to be perfectly balanced, the strings here have to hold a total of 2 newtons. So these together have to counteract the weight. And so if we were to look at it, then the tension on this one, since they're both perfectly up and down, would be 1 newton, and the tension on this one would also be 1 newton. That way, we have a total of 2 going up and a total of 2 going down. If these are perfectly horizontal, or sorry, perfectly vertical, parallel, then they will have the same amount of force on each of them. So the forces distributed along the strings would be 1 each. So now, what happens if they're at angles? Let's see, so let's erase this. I'm going to erase this. And so now, let's pull these at angles. So now the counteracting is here. Let's make it pink. So this is now 1 Newton, and this is 1 Newton. And what you should notice is that these form the hypotenuse. So what happens is, as the angle increases, so we're talking about this angle, as the angle increases, the force, tension, increases. So as the angle increases, the tension force also increases. So anyone who lifts weights or you've lifted things, you know that you want to lift with your arms as parallel as possible. Because if you start holding outwards on the bars, then you're going to have to start pushing with more force to lift those weights because you're going at a larger angle. So as the angle increases, the tension force also increases. Now, if you were to go to a 90-degree angle, you would actually not be able to do that. Every string that you can see is never actually perfectly horizontal if it's attached to something. There's always at least a little bit of a dip. And it's because you're actually approaching infinity if you want to think about it that way. But don't really worry about that. Just realize that as the angle increases, the tension force also increases.